So in this video we're picking up where we left off on the last one. We're trying to find the area under this function y equals x squared. We had in the previous video drawn this graph, and we're finding the area of this blue shaded region here. So we are using the limit, or the Riemann definition to find the area. The limit as n goes to infinity, f of x sub I, delta x sub I. And what we need to find are the x sub i's and the f of x sub i's. All of the delta x sub i's, we should make note, are the width of all those intervals, and the intervals, the entire region is 2 units wide, and we're dividing it into n pieces, so that's what the delta x sub i's are. So what about the f x sub i's? So the x sub i's, what this means is we're taking the interval 0 to 2. So let's write that, or show that here. So here's 0, here's 2, and we're dividing it into n pieces. So as we noted, each piece has width 2 over n, so first x1 we move over to 2 over n, and then the next time we move over 2 over n more, so that's 2 times 2 over n, which we have noted here, and then we keep moving over 2 over n times the number of times we moved over, so when we get to the ith interval, it's I times 2 over n that we moved over. That's our x sub I. So do you see the pattern? X sub 1, it's 1 times the width, 1 times 2 over n. X sub 2, it's 2 times 2 over n. X sub I, it's I times 2 over n, and we've got that repeated over here. So 1 times 2 over n, 2 times 2 over n, I times 2 over n, n times 2 over n. So those are the values that we are plugging into our function. So if we plug these x values here into our function is x squared. So we're just squaring the xi value. So we square 1 times 2 over n. That's the same as squaring the 1, so that's 1 squared, and squaring the 2 over n, 4 over n squared. In the next case, we're squaring 2 times 2 over n, so that's the same as squaring the 2, and then again we're multiplying by 4 over n squared, then we're squaring the I times 4 over n squared, then we're squaring the n times 4 over n squared. So let's put that together on the next blackboard to see what this expression here looks like. So we've got that written out. Here's the f of x1, the 1 squared times 4 over n squared. Here's the f of x2, 2 squared times 4 over n squared. The f of xi, I squared times 4 over n squared. The f of xn, n squared times 4 over n squared, and they're all multiplied times the delta xi, which is the width. It's 2 units wide, this interval from 0 to 2, where we're dividing it into n pieces, and so all of the delta x sub i's are 2 over n. And we've got this written in a form now where we can factor out lots that is common. So let's notice that every one of these terms has a 4 over n squared times a 2 over n common to them. So we can factor that out of every term. When we factor the 4 over n squared times 2 over n, which multiplied together is 8 over n cubed, out of every term, what remains in this term is a 1 squared, and this term is a 2 squared, and this term is a I squared, and this term is a n squared, and so that is this. So that sum, 1 squared plus 2 squared plus dot 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 n squared, we've written up here, we've written it in its summation notation. It turns out to have a sum in a closed form, n cubed over 3 plus n squared over 2 plus n over 6. And so we're going to substitute that expression for what we have in the braces here. So we've done that, and what we're going to do before we calculate this limit is to multiply out these three terms, multiply the 8 over n cubed across those three terms. When we do that, we get this expression in the line below. So we've got this expression here, and we're able to take the limit now as n goes to infinity. As n goes to infinity, this 8/3 term is unaffected because there's no n in it, so we just get 8/3. And then for these next two terms, they have an n in the denominator. N is going to infinity. The denominator of both those terms is getting bigger and bigger and bigger, and so those two fractions are going to 0, and we get our result 8/3. And if you'll recall from the last video, that's what we got by doing the definite integral. So I'll put the definite integral step in here. Right, you recall from the last video, we take the antiderivative of x squared and get x cubed over 3. We evaluate it between the a and the b, which we designate with this vertical line, giving us 2/3 minus, or 2 cubed over 3 minus 0 cubed over 3, or the answer we were looking for, 8/3. And so going back to the previous slide, where it's a little cluttered now, but we were doing the Riemann limit definition to find the area under y equals x squared. And we needed to first find the xi, so x1, x2, xi, xn was in this column. 1 times 2 over n, 2 times 2 over n, I times 2 over n, because we were moving on the interval 0, 2, right, dividing it into n pieces, so we moved 2 over n once, 2 over n twice, 2 over n, etc. And then we plugged that into the function y equals x squared, so we square each of these expressions, and we plugged that in and got all of these terms, kind of cluttered, but as you recall, right, each term had this in common, 4 over n squared times 2 over n. We factored that out, the 8 over n cubed, that left this expression 1 squared plus 2 squared plus n squared. We had closed form result for that. That gave us a limit of this form. It gave us this limit, which was easy to compute because only the last two terms had an n in them, and those two terms both went to 0. So this went to 0, and this went to 0, and we were only left with the 8/3. So we've actually calculated a Riemann sum, the limit of Riemann, a Riemann sum. That's in general extremely difficult to do. We wouldn't even want to try and do it in most. In the typical case, we would do it. We just do it this way with the definite integral, but we wanted to show it once with the limit of Riemann sums to show that we actually get the same result that way. So that concludes this video of doing a area using the limit of Riemann sums, doing it the long way.